Hello, and welcome back to our series on Vertex Operator Algebras. Today, in our 27th episode, we'll investigate some of the formal details of the formal sums that we began discussing last time. You might recall from last time that a formal series over a vector space V contains maps from the underlying field F to that vector space that we notationally write as a sum. These formal sums over F have many important subspaces, namely the Laurent polynomials and the formal Laurent series, both of which can be thought of as sums over the integers, with the former, of course, being finite. These formal sums, of course, are really meant to act akin to the operators of quantum field theory, and so the real action lives in the formal sums associated to endomorphisms of a given vector space. But first things first, let's talk about families of endomorphisms of V. Let x sub I represent a family of such endomorphisms, indexed by some set I that may or may not be infinite. Such a family is said to be summable if, for every vector little v in V, x sub I on little v equals 0 for all but finitely many I. Now, let's consider a family of formal sums of endomorphisms. We've got two potentially infinite things to keep track of: members of the family, indexed by I, and coefficients of the formal sum, indexed by, say, n. In this case, we'll use the function notation to say that little x sub I of n is a coefficient for z to the n. We say that the sum of these operators, a sum over the family index, exists if for each value of n, the coefficient z to the n is summable, which means, as we just defined, has finitely many non-zero terms. Finite families are summable by definition, so a lonely family of one operator, x, certainly exists. Having discussed potentially infinite sums of operators, we now turn to their finite products. Hopefully this rings familiar from the study of tensor products. To that end, consider a finite family of operators x sub I, where I ranges from 1 to r. We say that the product of these operators exists if every coefficient of z to the n is summable. In case it's not clear, such a product is also an operator, that is, a formal sum over the endomorphisms of V. Now, a quick word of caution about the products of operators. They don't work quite like your algebraic intuition would naively expect them to. Here's a great counterexample. Consider the product of two formal sums, the first over all non-negative integral powers of z, and the second over all non-positive ones. The coefficients from V in both cases is always unity. This product does not exist because, for example, the coefficient of z to the 0 is not summable. Indeed, 1 appears infinitely many times. However, multiplying the entire series by 0 enforces the summability rules by fiat. And thus, while the three-factor sum product exists, its subproduct does not. Just something to keep in mind. We can and will generalize these ideas to multiple commuting formal variables, where, just with a multivariate polynomial, the coefficients here are, again, taken to be members of the associated vector space. For formal sums of endomorphisms, we again use the function notation, as for m and n here. Now, one more piece of this formal calculus to contend with. Given some operator in two variables, z1 and z2, we say that the limit where z1 goes to z2 exists if the associated coefficient of the new, reduced monomials are all summable. FLM gives a specific formula for this. Note that in this calculation we're effectively integrating out the second factor of z term by term, which is to say that you might get a better intuition for what happens here by considering this final result term by term. Of course, we can extend this naturally to multiple formal variables. Now, here's a little insight from the physics or conformal field theory side. These operators are analogous to quantum field operators in a CFT. And in conformally invariant quantum field theories, there are no length scales to speak of, by construction. This makes doing any sort of epsilon delta kind of analysis, what we often do when we take limits in metric spaces, quite tricky. Despite that fact, we are still interested in what happens when operators collide or collapse to the same point. In quantum theory, we worry a lot about normal ordering of fields in this context. And normal ordering is hopefully something familiar to us now, as we've already learned about it in Chapter 1. Namely, the zeroth Virasoro generator had to be ordered in a special way to ensure that it was well defined. From the perspective of these operators, or formal sums of endomorphisms, we're going to need to worry about the same kind of ordering amongst the individual formal variables if we're going to allow for these limits to exist. And of course, we'll discuss that later as needed, but we're just giving you a heads up for now. While a lot of this has been super technical and detailed today, we can summarize all these requirements by observing that all the coefficients in any sum, product, or limit of such operators must be summable in order to exist. Finally, we end on some miscellaneous algebraic fun facts. First fun fact: there is a natural product of Laurent polynomials with coefficients in some vector space V with the formal series in F. That brings us back to the space of formal series over V. You can best think of this as being induced by scalar multiplication, as well as the natural inclusion of the formal variable multiplication from the Laurent polynomials into the relevant space of formal sums. The same is true when we consider products of those Laurent polynomials with the formal Laurent series in F, which brings us to the formal Laurent series with coefficients in V. This sort of natural product implies that the formal sums over F can serve as a module for the algebra of Laurent polynomials, and as a result, the formal Laurent polynomials are a submodule therein. That alone is just kind of a fun intellectual construction, but will pay dividends down the line. Hopefully this is all clear from context and discussion above, but when we take the limit of two separate objects formed over two separate formal variables, the product, assuming it exists, lands in the appropriate space. Phew! Wow, what an episode! What a mass of details! Let's summarize these from a physicist's point of view. Infinities plague quantum field theory, but not all infinities are bad. Formal series gives us a technology to work with them, at least in the context of conformal field theory. So that's our show, finally. Next time, we're going to take a look at one formal series in particular, the so-called delta function.